Hylozoic Soil, Musée des Beaux-Arts de Montréal, September to December 2007. Hylozoic soil offers patterns of motion by mechanical components that respond to occupants' movement within the environment. It is an interactive geotextile mesh environment that senses human occupants and responds with air movement produced by peristaltic waves of motion within distributed fields of lightweight pores. Occupants move within the Hylozoic soil structure as they would through a dense thicket within a forest. Microprocessor-controlled sensors embedded within the environment signal the presence of occupants, and motion ripples through the system in response, pulling trickles of air through the mesh and drawing stray organic matter through the arrays of filters. Machine intelligence is embedded within networks of microcontrollers that coordinate arrays of proximity sensors and kinetic actuators. Arrays of capacitance sensing whiskers and shape memory alloy actuators are used to create a diffuse peristaltic pumping that pulls air and organic matter through the occupied space. The microprocessor-controlled system includes Arduino hardware extended by new control boards, shape memory alloy actuators, and space sensors arranged in a distributed interactive system. Lightweight lattice and geodesic organizations form a structural core, employing digitally fabricated lightweight scaffolds that house distributed networks of sensors and actuators. The structures are designed at multiple scales, including custom components, intermediate tessellations composed of component arrays, and general structural systems. Several levels of behavior are programmed into the sculpture in order to encourage coordinated spatial behavior to emerge. Software is organized into local behavior, affecting isolated groups of devices, coordinated behavior between neighboring groups, and global behavior, running throughout the whole system. Each board produces its own response to local sensor activity and listens for messages from neighboring boards, identified by means of an address map of the devices within the installation, encoded into the software. The bus controller has information about sensor activity from all of the individual boards and is able to control a third level of global behavior with this information. Processing for the system is based on Arduino, an open-source platform that was designed to make tools for software-controlled interactivity accessible to non-specialists. The palm-sized Arduino microcontroller board can read sensors, make simple decisions, and control devices. In Hylozoic Soil, each board is paired with a custom daughter board that provides extended functions, including communication, high current outputs, and configuration switches. The distributed system consists of 38 controller boards, all with identical hardware. Specialized functions are assigned by software setups in groups of boards, and one board assumes a supervisory role for the entire system. Individual boards all talk on the bus controller's receive line and listen to the controller's instructions on the parallel send lines. Information is transferred from board to board via the controller. Breathing pores are composed of thin sheets shaped into outward branching serrated membranes, each containing flexible acrylic tongue stiffeners fitted with monofilament tendons. The tendons pull along the surface of each tongue, producing upward curling motions that sweep through the surrounding air. The structural core of Hylozoic soil is a flexible meshwork assembled from small, acrylic chevron-shaped tiles that clip together in tetrahedral forms. These units are arrayed into a resilient, self-bracing, diagonally organized space truss. Curving and expanding this trusswork creates a flexible grid shell topology. Columnar elements extend out from this membrane, reaching upward and downward to create tapering suspension and mounting points. Fitted into this flexible structure are hundreds of small mechanisms that function in ways akin to pores and hair follicles within the skin of an organism. Swallowing pores occur in a triangular layout that creates a dense series of openings running throughout the meshwork. These openings contain pivoting arms in triangular arrays that push out radially against the surrounding mesh, producing expanding and contracting movements. Simplicity and economy are prevailing qualities that have guided the design of the system, supporting massive repetition and efficient mass manufacturing of assemblies. Consumption of materials is reduced to a radical minimum by employing optimized, form-finding design methods. Strategies include use of efficient tensile forces in textile systems in mesh and shell forms, and derivation of three-dimensional forms from thin, two-dimensional sheets of material. Space-filling tessellations and nested components derived from sheet goods contribute to this hybrid economy. Some 8 cubic feet of acrylic polymer, 50 pounds of copper wire, aluminum sheets, and handfuls of specialized alloys are expended, while the expanded space formed from these materials occupies some 8,000 cubic feet. Mechanism is a central term of reference for this work, drawing upon new disciplines of mechatronics and artificial intelligence, integrated with applied technologies of industrial design and digital manufacturing. The parallel term empathy draws upon aesthetic theory that examines nuanced relationships involving projection and exchange. The broad tradition of organicism forms the context for this project. In this work, we strive to revise a common understanding of organicism as a late Romantic mode opposed to modernism, and instead renew the sense that this movement is an ongoing tradition deeply embedded in the 20th century and contemporary culture.